Welcome to Toddcast number 39. Next to the last one we'll do for alkenes, chapter 8 in this semester's lecture series. Tying off the last of the alkene reactions, and it may seem like it's never ending considering how many videos we've done, but I will tell you it is in fact ending. We have 3 to go. One is going to be an anti-Markovnikov addition, so ratio-specific or anti-Markovnikov addition of H in a halogen. So we'll look at HBr, but it could be any hydrohalogen that works. We're going to go from there to adding another oxidizing reagent, which gives us a diol. Before with epoxidation, followed by acidic water, we got an antidiol. This one we're going to get a syndiol. And then finally, something called ozonolysis, which will just be kind of a funky, cool way to break a double bond, generate some carbonyls. By the time we finish, we will have our spider charts all done and be ready to start looking at synthesis and just connectivity of reactions, how one reaction feeds into another. So with that in mind, let's start with our same compound. I've been doing this for over and over, and that is 2-pentene with a 2-methyl on it. So 2-methyl, 2-pentene, asymmetric in the sense 2 substitutions on the left, only 1 on the right. So we have a less crowded carbon. This is going to be key because, again, as I look at this reaction, I note that unlike before where I said first one on goes here, second one goes on here, and we got an H going on here, H plus went on to the less crowded, and then Br attacked as a nucleophile over here. Notice it's opposite of that. And so the question is, does the first one going on choosing the less crowded site, is that what broke down and that the first one on actually chose more crowded? Or is this a change in mechanism such that the first one on is no longer H, but in fact Br? And the reality is it's the second one, which is why it's so important to know mechanisms, because the first one you add always goes on to the less crowded carbon. So this time, because of this peroxide, so peroxides, just like we did earlier with BH3 followed by peroxide, we got anti-Markovnikov. Peroxides do funky, weird things. So this peroxide is going to force it to go anti-Markovnikov. So Br goes on first to this carbon. That's my first one to attack. That's my second one, gets attacked and gets an H. So the radical intermediate, which it's going to form, so we'll talk about radicals are in a second, extracts an H, and it does so on the more crowded carbon. So we're going to talk, just like we talked about carbocation stability, we'll also have something called radical stability. So radioselectivity, by all means, definitely, it's anti-Markovnikov. Goes the opposite of what we'd expect. So we usually expect H goes where H is. Now we're seeing H going where there were no H's. Stereoselectivity, none to speak of in this case, and I am getting Carl Center, but doesn't mean that we can't get some stereochem we'll learn about in the future chapter. But for now, we're going to say free radical chemistry does not come with any predictable stereochemistry. Okay, so the mechanism. The mechanism is bizarre. So free radicals, just as the name implies, it is a radical, meaning it has a single electron. Not sure if this is the first time you're coming across that word. We've brought up a few times. For the first time, I think it's present in the form of a reaction. Want to go back to chapter 1 or chapter 2, where we talked about homolytic cleavage, not hetero, where one atom gets both electrons, but homolytic cleavage, where they each get 1 electron. So this one single dot emphasizes that it's an unpaired electron. We know that there's a lone pair here, lone pair here, 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 and here, but it only has 7 valence electrons, and as such is highly reactive. So we did mention briefly what's known as an antioxidant. An antioxidant is something that can react with a free radical, and in doing so, stabilize it and cut down the damage it causes elsewhere. So we have free radical scavengers or antioxidants in our body designed to alleviate the issues with O2 biradical and the free radicals it creates in our body. That was mentioned earlier, kind of a cool bio side note. This one we're just going to do straight chemistry. So initially, with light or some form of input energy, could be heat, but it's almost always light, we break the peroxide. So as mentioned way back at the start of the class, we put peroxide in a brown bottle for exactly this reason. Because if it was in a clear bottle, the light from just ambient light that surrounds us would break it into free radicals, make a highly reactive solution that potentially could blow up. Okay, once you get this free radical, this single electron, it can react with an HBr. So when it does, it's going to pick up one electron from the H, leave behind one electron on the Br. So again, I want to emphasize that there are other electrons here, but we don't care about those. Those lone pairs are stable. So this Br has lone pairs here, but having this unpaired single electron makes it highly reactive. So this Br species is the one that's going to interact with the double bond. It is going to go on to the less crowded rather than the more crowded carbon. So the pi bond can break to give a free radical on this tertiary carbon, and then this free radical is going to come out here, where if I line it up the right way with Br, I can get a new bond to Br. So this carbon, less crowded, picks up the Br because the Br is first to attach. Just like we worried about carbocation stability, tertiary being really good, same is true for free radical stability. Tertiary beats secondary. So the free radical would rather be on the tertiary site. So you have this. This is now an unstable molecule. It can react with an HBr. Unsuspecting HBr is nearby. This free radical can come and pick up an H, just like happened here with peroxide. So the peroxide, I don't need much. It's called an initiator. I just have to add just enough to trigger a few HBRs, and then it becomes a cascade. This sort of does first the bromine adding the double bond, and then the free radical extracting an H from an HBr, regenerating Br free radical, which can now go in and react with another double bond. So it's this chain reaction that occurs. The key thing, HBr adds in an anti-Markovnikov fashion. Br goes on the less crowded carbon because it's the first one to add. The H goes on the second atom on, so it goes on the more crowded carbon. It gets the second choice. So anti-Markovnikov, because Br goes on first. So once again, it's still true. The first thing on will always choose the better seat, the better carbon. So we have one more for our spider chart, and that is if we do this reaction with HBr and peroxide, as opposed to doing it with CCl4, then instead of going on the Markovnikov carbon, it's going to go on the anti-Markovnikov carbon. There is no stereospecificity here, so know that it's anti-Markovnikov, but know that these two are diastereomers. This chiral center of the CH3 stays the same, but this one with the bromine changes. But reality is the H could have also gone in front instead of in back, so we could have also gotten this chiral center in back for both of these. So you get a mishmash of stereoisomers. So we could get RR, RS, SS, and SR. Key thing though is anti-Markovnikov, and the stereochemistry you just clean up later. Spider chart is complete. I'm going to call this the simple spider chart, the one that has a lot of the simple you get them reactions, nothing bizarre, and actually synthetically nice predictable outcomes. This other spider chart that we started was one that's going to be a few more complicated reactions. So I have altogether 8 on this one, and I'm going to have 4 on the other. So moving on to our next to the last reaction we'll do in this chapter, and that's permanganate oxidation. So KMnO4, rich in oxygen, so it is a great oxidizing agent, and then basic workup to get the molecule we want. But notice it is syn addition. Generally speaking, when we use a metal, it delivers both atoms at the same time. So a metal with H2 delivered 2 H's at the same time. A metal with a bunch of O's delivers both O's at the same time. And again, because it's syn addition, when they add at the same time, you get syn addition. It can be from bottom or top. So we can have KMnO4 coming from the front side or the back side. And because this is a chiral center, that distinguishes one from the other. Again, this is not because I chose the molecule as such, but this one is. So I'll get enantiomers. So I'll get 1, 2, 3, but H is in front, so S, and then 1, 2, 3, but H is in front, so R. So I'll get equal parts S and R, 50% of each. Optically inactive because it's a racemic mixture. Both OHs add simultaneously, meaning Mn must deliver them from the same side, so it's syn addition. And then eventually this OH minus is going to come in, displace the Mn, so those electrons will break away, and these O's that came from the Mn will now become OHs. So we'll look at this mechanistically. Ratio selectivity, you're adding the same thing to each side, so it's inapplicable. And stereoselectivity, syn addition, adding at the same time, so therefore you add to the same side, syn. One note that there is also a synonymous reaction, and a lot of times as you get further along in OChem, you'll notice there's 2, 3, maybe even 4 different reactions that carry out the same thing. It's specific for conditions. So here we need cold temperature and basic conditions to make this go. But if you have something that is, I don't know, sensitive to base for one reason or another, there's this reagent OSO4, which does the exact same thing. And very, very similar mechanism. It's just you don't need basic conditions to break it apart. So the permanganate mechanism works as follows. MnO4 has this, and you might even argue it's the O minus that attacks because of different resonance structures. If that kicks in, that kicks across, kind of the same thing as the O minus attacking. But this is going to be an electrocyclic process. This is going to sweep out to get an O. That's going to go to Mn. These electrons are going to go to that carbon. And you'll end up with this phenomenon. So I did it actually flowing the opposite way. Doesn't really matter. So these pi electrons between Mn and O will attack this carbon. This will go here, and that'll go across. And I'd done it the other way just so that it was actually attacking secondary. It really doesn't matter. It's a coordinated complex. Both O's are going on simultaneously, clockwise or counterclockwise. You could never tell anyway. So we do have this electrocyclic process, which then results in a permanganate coordinated to the double bond. So you know the alkene double bond's gone. You now have a sigma bond. This MnO pi bond's gone. You now have a sigma bond. And this one's gone. You now have a sigma bond. So resorts in this, I've marked the 2 O's in blue to distinguish them. The base will then come in. It attacks the Mn, breaks that apart. You can do it at both locations. So this will now pick up an H. And then same story. This Mn, this OH will come in, kick that. And so I should note that I'm being lazy. And let me say 2 steps instead of 2x. Explain what I'm doing. The 2 steps would be same thing as before. OH minus attacking in, step 1. And then that O picking up an H from water like it did here, getting protonated and ending up as an OH. So the mechanism, it's general, it makes sense. It's syn addition. The key thing is just that you recognize that when it's syn addition, when you have a metal and delivers 2 things at the same time, delivers it the same side. This is going to be the same story. Same basic intermediate, same basic breakdown. Mechanistically, not going to worry about it, but I am hopeful that you understand that there is this intermediate along the way. And you'll notice, even though electrons moved around, no charges occurred because wherever it started, it came back around. So this lost electrons, but then gained them back in the end. So in electrocyclic, you're not moving charge, you're just moving electrons around a ring. So building spider chart, I have 2 more to add. The first one, KMNO4, done cold in basic conditions, forms a syn diol. So notice that they are both back or both in front. They're enantiomers. You get a 50-50 racemic mixture. And then also we have the OSO4 version. And we use hydrogen sulfide, sodium and hydrogen sulfide to cleave it. So it's still something attacking the metal, in this case osmium, to break it down, we get the same thing. So again, depending on conditions, if you're base sensitive, you can get away with the amphoteric molecule up here. So only one more and our spider chart is all done. And that is ozonolysis, saving the best and probably arguably the most challenging, convoluted one till last. As always, I'm going to present a combination of chemicals that may or may not be actually what you see on homework and what you see on the test and in the book, because there's different ways of doing this. But generically speaking, then, ozonolysis involves using ozone to cleave. So it ends up that you have three O's, one ends up on this carbon, one ends up on this carbon, and one ends up on sulfur. If we use the version with zinc, then one would end up on this carbon, one on this carbon, and one on zinc in the end. So whatever you're doing to, or whatever compound you're using to get oxidized, remove that third O, it's just ultimately going to pick up the third O of ozone. So I actually want to start by just, instead of mechanism, just going over the basic gist of this. O3 adds to the sigma bond, or the pi bond, excuse me, and ultimately inserts an O into the sigma bond. So initially it's going to add to the pi bond, but it's going to break the sigma, breaks the pi first, sigma second. So I'm going to draw this bond being cleaved, and they both end up with O's. And then that's my third O over here. So it's important to pay attention to where the O's are going. This compound, dimethyl sulfide, reduces down the third O, so it itself gets oxidized, but it removes the O and ultimately allows the two carbonyls to form. So because this had two R groups, we get a ketone. Because this has an R group and an H, we end up with an aldehyde. So usually you just cleave it, nice and simple. Regioselective, nope, not applicable. Stereoselectivity, no chiral centers. So this one is just straight destruction. You cut it in half, add a couple O's, but you've done chemistry. So useful shortcut, draw that line between the double bond. So this is the breakage line. Pull them apart and add some O's. So nice and straightforward, really simple type of reaction to visualize. Mechanism, maybe not so much, but the utility here. So this is going to be really useful when we start doing synthesis, because it's a way to break a carbon-carbon bond, which generally isn't easy to do. And this will couple with chapters 12 and 19 when we deal with alcohol to carbonyl oxidation, and then also in chapter 19 we just deal with carbonyl reactivity. So aldehydes and ketones are carbonyls. The mechanism, absolutely bizarre, and you have to know it. Ozone has two major resonance contributors. They each have a negative on one of the ends and a positive on the O in the middle. So I can kick those electrons in and they could go over here, and so I'd have negative on either end. So it's an O plus in the middle with O partials, minus half and minus half, if you will, at each end. Because it's symmetric, it doesn't really matter like what the double bond is. It could be either end reacting with a less crowded site. So if this one goes in, that can kick up here, and that can go in that electrocyclic fashion. So with this electrocycle, the system of having electrons move around is working. So this negative comes in and attacks the less hindered. This comes out to this O, it breaks this pi bond, which puts electron density on the middle O. So we now have this system right here. And I want to figure out where it's going to go from there. So it's a dual peroxide, which is highly unstable. This next maneuver is going to be really, really bizarre, and it's worth numbering the system to track when you do this on your own. But we're going to insert one of these O's into this sigma bond. So weird as this may be, this O right here, this bond is attacking this O and knocking the bond from O to O to form there. So if I draw it just right, I should see something like this. Let's leave all the atoms in the exact same place. So this O are these two, but now it is bonded. When this bond broke, this carbon now became bonded to it. So this is here. And this bond that was from O to O used to be a bond here, that moved to right here. So if I look at it, this was a carbon to O to O to O to carbon ring. It is now a carbon to O, like it was before, but now to carbon to O back to carbon. So this equals this. Notice that this O is a bridging one. Notice that these two O's are connected here. This is the key player. This is not easy to see, but I made it a point. These carbons and these three O's do not change their location. These three O's are in the exact same spot, these two carbons exact same spot, but the bonding connectivity of electrons has moved. This again is known as electrocyclic. Electrons are moving around in some cyclic system. I have rearranged it. I've moved this O, rotated it up so it's easier to see. And now it's just going to be a simple electrocyclic again that is going to save us. So sulfur is going to somehow get an O, which means it is going to have to donate a lone pair to O and receive a return electron pair from O. I coordinated it to be with the black one, the black oxygen, so the two blue ones will stay on the carbonyls. So in no definite order, I'm going to say this sulfur attacks the O, which becomes an extra bond O, which pushes those electrons in here to form a pi bond. Too many bonds of O, so that kicks over here. Too many bonds of O, so therefore it kicks that set of electrons back to the S. They eventually end up back in that spot. So you end up with, and again, I want to keep everything in the same place. Notice these two with a double bond to O now. These two with a double bond to O. This O that's right here is now bonded to the sulfur. So I kind of move sulfur a little bit. But hopefully you see that this is the ketone, this is the aldehyde, and this is the oxidized sulfur. So, very complicated mechanism. I want you to go back for each of these and draw them from scratch. Try to draw them from memory and play along the video, because if you know the mechanism, that's step one. For every one of these, you're going to have to be able to predict the product, write a mechanism, or come up with a synthesis. So our last reaction for our completed spider chart, ozonolysis, ozone dimethyl sulfide, so DMS is what we just used. Again, you can use zinc, zinc with peroxide, zinc with water, DMS. Have flexibility, be able to write alternatives to the exact step here. It has to be O3, it has to be ozone for ozonolysis, but your workup reagent, your reducing agent can be different compounds, but I'll go with DMS for this. Again, it's going to cleave that, and when it does, it opens a ring. So let's just make sure I understand this. This is 1, 2, 3, 4, 5. I'm not numbering nomenclature-wise. I'm emphasizing that 1 had a CH3, 2, 3, 4, and 5. 5 ends up having an H. So that's why 5 has an H. So it looks good. It works. Our spider chart is complete. This is the 4 reaction one. You also have the 8 reaction one. So altogether, you're going to have 12 reactions to cling to know their mechanism, to know some variations, to know how to use them in synthesis, to know how to use them in predict the product or predict the reagent, whatever way it's asked. But it is information overload probably at this moment in time, but the puzzling will kick in. It'll start being enjoyable soon. So, end of that spider chart. We have one more thing to do in this chapter, and that's apply all this information. But hopefully for now, this is falling into place. Go back and watch whatever you need to over this last series. A lot of information, very, very fast. In lecture, we're probably just going to do the same thing, go through the reactions, but I might toss a few examples along the way as well. Thanks for watching, and I will see you in class soon. Bye.